Hello physical science students, and welcome to our video about the electromagnetic spectrum. You're all familiar with electromagnetic waves now, and some examples would be your cell phone using electromagnetic waves, x-rays, and sunlight. But you also know that you would not take a picture of a broken bone with your cell phone, and you certainly wouldn't use an x-ray machine to text your friend. So, what is the difference between these kinds of electromagnetic waves? Well, you can see on this diagram that different electromagnetic waves, different types of waves, have different amounts of frequency and different wavelengths. Remember, when we have greater frequency, the wavelengths are shorter. And when we have longer wavelengths, we're going to have a decrease in frequency. Frequency and energy are also related. The higher the frequency, the greater the energy those waves have. We are going to talk about some of the different sections in the electromagnetic spectrum. It's divided into different sections, and each of those sections have a certain range of frequencies and therefore have specific properties. So let's start by looking at radio waves. And on our little diagram, the radio waves are clear on the far end. They have the longest wavelength. Radio waves are considered to be electromagnetic waves that are longer than 10 centimeters in wavelength. So therefore they have very low frequencies and their photons have very low energy. A couple of different types of applications for radio waves: audio transmission, you know about that. Radar, which is similar to sonar, except that with radar, radio waves are transmitted toward an object, and by measuring the time required for the wave to bounce off that object and return to the receiving antenna, the object or the location can be found. Radar is used for tracking the movement of aircraft, watercraft, spacecraft, and also law enforcement officers use it to measure how fast a vehicle is moving. MRI is another application for radio waves. It is a medical imaging device, and the patient lies inside this large cylinder, which contains a very powerful magnet and also a radio wave emitter and a radio wave detector. Then when the MRI is running, hydrogen atoms in the bones and soft tissues of the person behave like magnets, and they align with this very strong magnetic field. Some of the protons absorb energy from the radio waves and they flip their alignments. And the amount of energy that a proton absorbs and then re-emits depends on the type of tissue. So the radio receiver detects the energy and uses that information to create a map of the different tissues. Regardless of how scary it sounds, it is painless and it's not harmful. Now let's take a look at microwaves. They are a little bit shorter in wavelength than our radio waves. They are from roughly 0.1 millimeters to 30 centimeters. The microwaves that have the wavelength between 1 and 20 centimeters are generally used for communications. Microwave ovens, you're all familiar with those. They definitely use microwaves, and in a microwave oven, the microwaves interact with the water molecules in the food, and each water molecule has a slight positive charge on one side and a slight negative charge on the other side, so it will align in a magnetic field because it's polar. That vibrating electric field inside a microwave oven causes the water molecules in your food to rotate back and forth billions of times each second, and that creates friction between the water molecules and generates thermal energy, which cooks your food. So why don't I cook my ear off when I talk on my cell phone? Good question. Realize all of these waves we're talking about are electromagnetic waves, so they're all similar to each other. The main difference between them is their differences in wavelength and in frequency. And the microwave oven, although it's in the microwave region, is using the EM waves that have higher frequency and higher energy, whereas cell phones are using the higher wavelength, lower frequency, lower energy end of that spectrum of microwaves. So remember the last time you stood by a campfire and you felt that warmth being transmitted to you. was actually being transmitted by infrared waves. Infrared waves are electromagnetic waves with a wavelength between 1,000th to 700 billionths of a meter. Now, actually, every object emits infrared waves. Here is an infrared image of a cat. We also use infrared waves to operate things like CD-ROM drives and TV remote controls. And that brings us to visible light. Visible light differs only from radio waves, microwaves, and infrared waves only by its frequency and wavelength, and also energy. Visible light is in the wavelength range of 700 billionths to 400 billionths of a meter, and we're right here. And if we expand that view right here, we are looking at the wavelengths in meters. This is another expanded view looking at the wavelengths in nanometers. Also gives the frequency in hertz. The brain, actually, our brains, interpret different wavelengths as different colors. When all colors are present, they appear as white light. So now let's take a look at ultraviolet waves. We've moved just beyond our visible spectrum, and we're increasing our frequency a little bit and energy. Our wavelengths are decreasing. Now we're in the 400 billionths to 10 billionths of a meter. Some useful things that we can do with UV waves. One is purifying food or water. When ultraviolet light enters a cell, it damages protein and DNA, and for single-celled organisms, this is fatal. So it can be used to purify water. It can also be useful because UV waves make some materials fluoresce. In other words, materials that fluoresce will absorb the UV waves and re-emit the energy as visible light. And here's an example of that being useful in forensics labs. So you all know that UV waves, ultraviolet for UV, are harmful. A lot of exposure to those is not healthy. However, you do need some of it. The UV waves, when they strike your skin, enable your body to make vitamin D, which is really important for healthy bones. The ozone layer, and you all know this, is wonderful at protecting us from the most damaging of UV rays. Most of the UV waves that end up reaching our surface are the UVA rays. They are the longer wavelength UVA, and they do not have as much energy. Not very many of the UVB rays end up reaching the Earth's surface thanks to our ozone layers, and then none of the even higher energy UV rays end up reaching the Earth's surface. So the UVB rays are the primary cause of sunburn and skin cancers, although UVA can contribute to those as well. So let's take a quick look at how the ozone layer is damaged. The ozone layer is critical for life on Earth. Without it, we would have no life on this planet. But when molecules like chlorofluorocarbons, the chlora is for the chlorines, fluora for the fluorine, and carbon for the carbon atom in that molecule, when those enter the stratosphere, where our ozone is, the UV will end up causing one of the chlorine atoms to break away from that CSC molecule. And that free chlorine atom hits an ozone molecule. Ozone is 3 oxygens bonded together. When the chlorine atom encounters the ozone, it will pull one of the oxygen atoms away from that ozone, breaking the bond, and we no longer have ozone. We simply have oxygen. That is how oxygen likes to go around in a pair like that. That free oxygen from the stratosphere hits the chlorine and monoxide molecule right here and breaks the chlorine or atom free, and it is free again to go and hit another ozone molecule and repeat this cycle over and over and over in the stratosphere, depleting the ozone. So now we're moving on to the electromagnetic waves in the section called X-rays. They have wavelengths that are 1 billionth of a meter to 10 trillionths of a meter long. much shorter wavelengths than UV waves, and their photons have even larger energies. Here we have our X-rays on our diagram. X-rays penetrate skin and soft tissues, but not denser materials like teeth and bones. And that's why they are useful to form images like this one. And that brings us to our last type of electromagnetic radiation, and those are gamma rays. They have wavelengths that are shorter than 100 trillionths of a meter. They have the highest frequencies and the highest energy photons. They even have enough energy to penetrate several centimeters of lead. Both X-rays and gamma rays are used in a technique called radiation therapy. Cancer cells can be killed with very carefully controlled beams of these rays. Some advanced ideas: research the history of the development of the microwave oven or any other piece of technology that is interesting to you. Investigate additional uses for infrared radiation. What enables the human eye to differentiate between the different wavelengths of visible light? Other questions you might have. Feel free to ask your own questions and do a little research, and I look forward to seeing you in class.